Hello everyone and welcome back. My suspicion is that this video will probably be the shortest video of the entire series because we really won't be learning any new procedures or techniques. The only thing that we will be doing is taking an old idea, the idea of the tangent line, which we've studied in so much detail, and just expressing that in some slightly different language. So today we're going to talk about what's called linear approximation, which is using the tangent line to approximate a function. So all the way back in video 00, we said that one of the main ideas of calculus was that it gave us a way to take something that was complicated, something that was curved, and replace it by a sequence of line segments. Now, how do we construct those approximating line segments? The key is to use the tangent line. For example, here on Desmos, we have this function that we studied back when we did implicit differentiation. And we found in that video the equation of the tangent line at the point 3/2, 3/2. Now, if I take this location 3/2, 3/2, and I zoom in very, very close at that point, there reaches a zoom level where the tangent line and the function are basically indistinguishable. It looks like I can barely tell them apart for x's which are within maybe 0.005 units of the point of attachment 3/2, 3/2. We can basically use the tangent line as a pretty great stand-in for this more complicated function. At least for x's which are close to the point of attachment, that approximation is going to be pretty darn good. Now what if I wanted to consider the behavior of the function at a location which was much further from that point of attachment? Maybe, for example, somewhere over here. Now at this location, this pink tangent line is no longer a very good approximation to the blue function. So what we would need to do is, if we were trying to approximate the blue function somewhere in this region, we would have to calculate the tangent line a second time. This time the tangent line may be at one of these points here. And by selecting points, maybe spaced 0.01 units apart on this graph, calculating the tangent line at each of those points, we can begin to get a linear approximation to the graph constructed by little baby segments of tangent lines. Something that would be tedious and difficult for a human being, but that would be completely manageable for a computer. To just take x values that are maybe 0.01 units apart, calculate the tangent line at each of those x values, and use them to construct an approximation by line segments. So at this point it becomes convenient for us to have a look at a general formula that could be used to find the equation of the tangent line to a function at a given location. Some general formula which sort of captures these steps that we've been doing over and over again in all these problems where we were asked for the equation of the tangent line. Now, in general, when we were asked for the equation of a tangent line, we had two things that we needed to figure out: the slope of the line and the point on the line, the point where the tangent line was attached to the graph. The slope of the tangent line, famously, is given by the output of the derivative at the given x value. In this case, we're just going to generically call that x value a. Meanwhile, the point on the line is given by x equals a and y equals f, the original function evaluated at a. So, based on this, what is the equation for the tangent line? It would be y minus the y of the given point equals the slope, f prime at a, times x minus a, x minus the x of the given point. Or if you prefer, sometimes we wrote this as f prime of a times x minus a plus f of a. This is the formula that I use all the time if I need to quickly write down the equation of a tangent line. For example, if I'm constructing a graph on Desmos, this is the equation that I have in the back of my mind, the one that I'm using. This is a really, really nice, really fast and convenient formula to use. Now, a word of caution. Sometimes students use this formula with their eyes closed. And sometimes students using this formula forget that at the end of the day, the equation of the tangent line has got to be the equation of a line. So here's a common error that I see. Someone sees this formula and they say, okay, suppose they want the tangent line at x equals 1 to the function f of x equals x cubed. So they say, okay, f prime of x is equal to 3x squared, and therefore the tangent line is equal to the derivative 3x squared times x minus 1 plus the original function x cubed. Now looking at this work, what is wrong here? What has the student done incorrectly in their attempt to use the formula in blue given above? The issue is that the student never plugged the given value of a into either the original function or the derivative. As a result, they obtained an equation which is not linear. This equation could not be rewritten in the form m times x plus b, because this equation is going to have higher powers of x in it. It's going to have an x cubed, and that makes it not linear. So what would the correct answer be? The correct answer would be 3 times 1 squared. X minus 1 plus 1 cubed. Because f prime of 1 is equal to 3, and f of 1 is equal to 1. Now the linear approximation formula is absolutely identical to the formula given above for the tangent line. The linear approximation to a function called f of x attached at a point called x equals a is given by a function which is usually called L of x. This is basically just replacing y. The other part of the equation is completely the same. So f prime of a, x minus a, plus f of a. Just a different way of referring to it, basically a synonym. Now linear approximation, actually the more I learn about things like physics and engineering, the more surprised I am by how heavily this tool is actually used in practice. I won't be able to actually show you a lot of the uses because understanding the applications kind of requires a lot of more advanced knowledge of physics, engineering, and of mathematics. So I'm going to try and show you just a couple of introductory uses of this linear approximation. Please have faith that more uses are out there. Alright, so here is the simplest possible use. We have a function e to the x squared. Now e to the x squared is a function that behaves really nicely at x equals 0. As a matter of fact, f evaluated at 0 is something that I can calculate by hand. E to the 0 power is the same thing as simply 1. The same thing is even true for the derivative of this function. F prime of x by the chain rule would be equal to e to its exponent times the derivative of that exponent, in this case times 2x. And so if I plug x equals 0 into that, I get something that in some ways is even easier. 2 times 0 times e. 0 destroys everything else, result 0. So now someone comes along and they say, actually, I'm not interested in x equals 0 right now. I'm interested in the case of what happens at a slightly different x. What happens at x equals 0.01? So let's go ahead and let's estimate the value of the function at 0.01 by plugging that x equals 0.01 into the linear approximation. Point 0.01 is pretty close to x equals 0, so the behavior of the linear approximation should be a pretty good representation of the behavior of the original function. In other words, the tangent line is going to be pretty close to the actual function's curve. So let's use this information about what happens to the function at x equals 0 to construct the linear approximation. It's just the same old same equation of the tangent line. So it's equal to f prime of 0. That's 0. X minus the given x value, also 0, plus the y value, the output of the original function, just 1. Now if we simplify this, we get that the linear approximation to the function is a constant function 1, which predicts that the value of the original function will be roughly the same as the value of the linear approximation will be approximately equal to 1. And in reality, that really is pretty close. The actual value of e to the power 0.01 squared is given by 1.0001. So the difference between the actual value of the function and the value predicted by the tangent line is only 0.0001 units. So here's another common exercise of a similar flavor. Suppose we have n and we have no idea what the number n is. N is just some number, and we're going to try and find the linear approximation to the function which is called x plus 1 to the power n. We're going to try to find the linear approximation, the equation of the tangent line at x equals 0 in particular. Okay, so if I plug 0 into this, then I get 0 plus 1, which is just just 1 to the power n. Now we don't know what number exactly n is, but it doesn't matter. 1 to any power equals 1. Okay, now what about the derivative? If I take the derivative of the function x plus 1 to the nth power, this is a great opportunity to use the power rule and the chain rule. The outer function in this case is blink to the power n. And by power rule, the derivative of that outer function would say n comes down, blank to the power n decreased by 1 unit. So in this case, what would f prime of x be? F prime of x would be n times blank to the power n minus 1. Then fill in the blank with the inner function x plus 1. Multiply that by the derivative of the inner function. But the derivative of x plus 1 is just 1, which really won't have much of an effect. So what happens if I plug 0 into this? Then I get n times 0 plus 1 to the power n minus 1. But again, when you raise 1 to any power, the result of that is 1. So f prime of 0 is equal to n times 1 is just equal to n, whatever number that has to be. So the linear approximation at x equals 0 would be given by the derivative at 0, which is the currently unknown number n, x minus 0, and then the output of the original function at 0 was given by 1. If I simplify that, the linear approximation would be given by take the number called n, multiply it by x, and then add 1. Now someone says, okay, follow-up question. Use the linear approximation to estimate the value of 1.001 to the power 17. Now, the question is, looking at this, what is the value of x that is going on in this estimate? Let's compare what we have here to the function f of x equals x plus 1 to the power n. Now, by comparing the exponents, I can see that in this particular specified expression here on the left-hand side, that n must be equal to 17. But now let's try and figure out what x is equal to by looking at the bases. If I compare 1.001 to x plus 1, then that would have to imply that x is equal to 0.001. So basically, I'm trying to estimate the output of this function f of x in the specific case that the exponent is 17 and at the specific location where x is equal to 0.001. So let's put both of those facts into our linear approximation formula. That the function's output at 0.01 is almost equal to the linear approximation at that same x value, which is given by n equals 17 times 0.001 plus 1, which is simple enough that it can be calculated by hand. All of this could be calculated by hand, remarkably. This would be 1.017. Once again, this estimate is pretty accurate. If I take a computer and use it to find 1.001 to the 17th power, then it chugs and it spits out 1.017, and then it has some other digits after that, 1, 3, 6, etc. So, rounded to 3 decimal places, this answer is an exact match to what was predicted by the linear approximation. Here's another example. Things like computational efficiency begin to become important when your programs get larger and larger and larger. If you're writing a large program, that is not efficient in computation, that's when you get stuff that looks like this.
Xylus BHM, thanks for 6 months. Welcome back. I should have said yes, but whatever. Oh yeah, I got perk points. So you're right. Yeah, it's like Chivalry, Mountain Blade style combat. Borgere. Uh-oh, not one of these.
It's quite slow to calculate square roots. And as a result, it can be quite slow to calculate distances when you're designing a game or something like that, because distance calculations require the square root. So let's see if we can replace the square root function by something that's linear. Let's find the linear approximation to the square root of x at, for example, maybe x equals 1. And then let's use that to estimate the square root of a more difficult number, like 1.002. So the original function at the given value of a is just the square root of 1, result 1. And the derivative of the square root, we've seen a few times, is 1 over 2 square root x. And therefore the derivative evaluated at 1 is given by 1 over 2 root 1 is given by 1/2. So the linear approximation formula, the equation of the tangent line, would be that slope of 1/2 x minus 1 plus the y value of 1. So what does our linear approximation predict? It predicts a value which is equal to 1/2, 1.002, take away 1, plus 1. Once again, this is actually so simple that even little old me can do it by hand. This would be 0.001 plus 1, which is 1.001, given by the linear approximation, which is roughly equal to the output of the original function. Let's have one final look at a linear approximation application. And let's use the approximation to sine of 3x at x equals 0 to try and figure out what's happening to the limit as x gets close to 0 of sine of 3x over x. The original function is given by sine of 3x. And if I plug 0 into that, I'll have sine of 0, which is equal to 0. Now what about the derivative? In this case, our outer function is sine of blank. The derivative of sine is cosine of blank. The inner function, 3x, fills the blank, and the derivative of 3x gets multiplied. So, f prime of 0 would then be equal to 3 times cosine of 0, which is 3 times 1, which is equal to 3. So the linear approximation formula is given by the slope 3, x minus a, plus the y value, which can be simplified just to 3x. Here is our linear approximation, which is approximately equal to the original function for x's close to the 0 value that we were given. Now in a problem such as the one given above, where we're calculating the limit as x approaches 0, when x approaches 0, it's basically getting infinitely close to 0. And the closer that x goes to 0, the closer the linear approximation and the original function become, until basically it's appropriate to remove the original function and replace it with the approximation, remove sine x and replace it with 3x. As a result of this, we can now simplify this expression. It's now rational, and it becomes the constant 3. That concludes today's material. We talked about the linear approximation, which was just another name for the tangent line. The name was used to acknowledge the fact that the tangent line can be used to estimate the original function at x values which are close to the point of attachment.